plus possibility. So it just sort of folds, keeping track of the frontier of possible things. And so in the end, you get a single list of all the solutions out. But the real beauty is that if you looked at the computation to produce that single list, the computation kind of looks like a tree. And because we're lazy, when we evaluate the first part of the result list, we don't have to compute the whole thing. We just compute the branch of the tree and all the backtracking needed to get to that first element. So just by being lazy, lists give us a nice backtracking search capability. And this is also relevant because one particularly good way to think about lazy data structures is as a way to reify computations. And you can think of a single list as actually more of a linear loop. So just, if you wrote like 1 through 10, right, and you wrote like sum 1 through 10, in a strict language, this would be equivalent to creating a list, 1, 2, 3, 4, 5, and so on, and then summing it. But in Haskell, what really happens, or what should happen, is that as you go along, you have this list, which is going to be, let's say, 1 followed by a thunk. And so when you get to sum, it says, well, I want 1, and I want the next element. So now we have 1, 2 followed by a thunk, and it adds these in its little accumulator. And then since there's no more pointers to it, the garbage collector can collect it, right? And then it evaluates the next element, 3, adds the work. That's not how summing works. But so actually, summing is even nicer because it only needs to consider one element at a time, and it has an accumulator. So it starts with 0, it adds 0 to 1, it gets 1, and then the garbage collector can collect this when we're done with it. And it forces the next element, 2, and adds it and so on. So really, in reality, only a handful of these elements are ever in memory at a time, and it works out to just being a loop that goes along with like a couple of variables and just keeps track of the sum. So in this case, we can see the list is the loop. And in the case of the fold, it's a little bit more complicated because we have a whole bunch of nested lists. But really, the way to think about, let's say, a list of lists is as sort of a nested loop. And if you actually went through and you tried to implement Prolog in an imperative language with for loops, like you would try to do this in Python with generators, you would actually see that the resolution algorithm ends up being this sort of nested loop, which I personally found a little bit hard to figure out until I played around with fold M. Okay. So if you're interested in the entire implementation, on my GitHub, I have a full sort of Prolog interpreter, which includes a few things I didn't talk about. And the whole, the core of the interpreter, minus the parsing, is 70 lines of code. So the whole thing is quite short. And if you want to look at it, it's just on my GitHub under Tikhon Jelvis /simple-prolog. Right. And so you can look at the code, or you can, of course, you can just try implementing it yourself first. I think it's quite a good exercise. And now I think the sort of, last thing, well, not the last thing, but one thing I want to talk about is type classes, right? So we remember what rules in Prolog look like. We had likes, Bob, X, given that X is a fruit, right? So now let's think about type classes. Let's think about type class instances, right? So we could, for example, we have an instance show S implies, that doesn't fit. We have an instance that says show S, then we get show list of S, right? And so this would just show the list. Actually, amusingly, I think this doesn't exist in normal GHC because show has an extra method for dealing with lists as a complete hack to make strings look pretty. So if you've ever actually looked at the show type class and you've seen that there's 2 extra methods, part of the reason is just this horrible hack. But the point though is if you take a look at instances, we can have preconditions and then we have a result. And so if you think of type classes as predicates and types as atoms, then you just get Prolog but flipped. So in fact, the little type class arrow is just the same as this arrow. And in fact, the Prolog, the subset of Prolog I just talked about is roughly equivalent to what you get at the type level with type classes. So a lot of these programs you could actually write. And I'm actually not entirely sure about how well some things work. So for example, I'm not sure about how trying to write a type class that just like a multi-parameter type class, which is like EQXX. I'm not sure exactly how well that works, but we actually have type equality built into the language now. So in the future,
I think actually the predicate that you're talking about is actually multi-parameter type classes. They feel like predicates even more than single parameter type classes.
Right.
So because there's like certain relationship between all of these arguments. So it's
So this is another reason that it's healthy to play with a bit of Prolog, is because overall it's a much more forgiving environment than Haskell type level programming, which takes at least some amount of like magic and getting through poor error messages and so on. And you can't just inspect it or debug it easily. So if you just play around with Prolog, you'll get a hang of thinking logically, and then you'll be able to apply it to type classes and do all sorts of crazy things. And in fact, I mentioned type level numbers in the slides, and a lot of the ways to actually make type level numbers practical involve having type classes which have recursive instances. So you have an instance for 0, which might just give you a value of 0, and then you have an instance of, you might say like n x implies n s of x, where n equals where n equals n plus 1 of like the appropriate type. I think you'd have to have a little bit more structure to it, but the basic idea again is that this looks a lot like the Prolog rule for numbers I talked about. And the other thing you can do with Prolog that's quite nice is you could basically take a Haskell AST that hasn't been annotated with types, right? And turn all of the constraints that we have, like for example, we know that 1 has to be, ignoring type classes for a second, let's run 1 as always an integer, for example, right? So by coming together with all of the sort of base constraints we know, and all the type signatures we know, if we just take that and turn it into a Prolog program, leaving variables for everything we don't know, it actually turns into Hindley-Milner. So you can get type inference just by expressing the types as a Prolog program. It's not super efficient, but I think for type inference it's actually fast enough. So has anybody sort of seen the style of inference rules in logic, right? Where we have some conditions on top, right? And then we have the result at the bottom. So for example, f of a has type tau or something, and then up here we'd say, well, if f has type anything or something to tau, and a has a type of something, then the result is this. Well, this again is actually just the same logic as Prolog. So if you sort of squint and you turn this sideways, and you replace the bar with the little dotty thing, you just get Prolog. So you can actually just take the inference rules that specify the Hindley-Milner type system, write them out in a slightly different syntax, and get a working algorithm for doing type inference and type checking. And also similarly, if you've ever seen operational semantics, they also use a similar bar notation. So you could take the operational semantics of a language, which specifies how it's evaluated, and you could write an eval function in Prolog. So for example, you could say, eval x, given that x is a number, and then you might say, eval f of x, eval like an application of f, so some function f to x, so on, given that f is a function. If you actually, the point is you could implement an evaluator, and the really neat thing is you could use it to evaluate a program forwards, but you can also use it to evaluate a program backwards. So you could say, well, I have the result of x and have this program, which inputs would give me x? And Prolog can do that sort of thing for you, because it's sort of bidirectional. And of course, the only sort of compromise is that when you do this for your evaluator, your program, instead of being run in like linear time, is always exponential. Okay. Okay.
Cool. All right. We're all out of time, so I have to kick everyone out.
What's your name?
Oh, Yosad. Yosad is next. So if you want to wait around.
Is the backtrack unification algorithm exponential already or not?
I think backtrack is I don't think unification solves this. But backtrack is, yeah. But the actual structure, we have a bunch of rules to consider.
Yeah.
No, I mean, unification seems like it would go like linear to like the structure.
Yeah, that's unification and the resolution.
The resolution. Yes, I think backtracking resolution is exponential.
Got to have that. Like any sort of like, oh, I'm take a shortcut. Nope.
And in Prolog, the way they solve it is they give you this cut over here, which sort of just tells you stop there after this point. And that's terrible because it breaks the abstraction of.
Yeah.
Oh, great.
You can't write past Prolog without it.
Yeah, just take it. I guess it lets you actually borrow this or finish it non-entity universe time.
So
yeah.
it's about giving it to me.
There's other logic languages that don't do cuts that are fast in some other ways, like analysis or like static typing, but I don't know how they work.
Yeah.
If you're interested, you can check out Berkeley.
I've heard of it.
Yeah.
Check it out.
So that one doesn't have copy. It's like a nice pure happy language, logic language, but and it does it by being like static type. I mean, static type is better.
There's something here.
Yeah.
Okay. Let's go. I would just say, let's go. Yeah, just everyone here. Let's just get in. And I'll call out other people.
There you go.
All right. Did it.
Well, does someone want to help me get this going? The like never use, yeah, like the projector. Like I got it plugged in. I'm sure.
Is that on?
Oh, it's don't turn it off apparently because then you have to wait for it to cool down and uncool down or something. So
Last talk didn't use it at all, so I'm guessing it was on.
they used it.
Oh, they did,
just
okay.
gave up. Oh, but it might be on.
Oh, so he's the one that turned it off.
Yeah, that was
It looked like it was
Oh.
having some issues.
It looks like maybe it was just the power thing. It was orange, which means it was like a standby baby.
maybe.
Yeah, I think it was off.
There was some dire warning.
Standby or whatever. Yeah.
I'll use the whiteboard a little bit of time too. That would be less than ideal.
Power low.
Okay, you're all here to learn about yourself, right?
Yeah.
Okay. How many of you have used yourself before at all? 3. Cool. How much? Like a lot, a little bit?
The only programming I've ever done is in Yosemite, period.
Okay. This might be too basic for you,
But I've never done any other programming, so I'm totally new at everything.
okay. So today I'm going to talk about. Oh, yay. I don't even need to move this stuff. It's just
I actually don't really understand how it all works. I don't understand how it all works at all.
how it all works. Okay. Well then, today you're going to learn it. All right. If I ever get this presenting on, do I have to like drag it over to the other window?
How did you decide that that was the place to start in programming?
Yeah.
Because I'm working on a project with somebody else who's the programmer, and he got me into getting involved in the programming side of it. He decided to make it in Yosemite.
People would take that route into programming.
You got very lucky.